The main concept in Chapter 2 is that of the slope of a curve at a specific point. This allows us to determine how much something is going to change at an exact moment or an exact value. In order to develop this concept, we're going to later define something called the derivative of a function, and inside the derivative definition is the concept of something called a limit. As a matter of further explanation of this same idea, consider a simple graph, perhaps something like this cubic function here. If we wanted to know the slope of the line tangent to the graph at a certain point, so say this point here, we need 2 points to find slope. So we could pick 2 points, perhaps here and here, and find the slope of that line, but it's not at the exact point we want. So we could then move a little bit closer and find the slope between those 2 points. But again, we want the slope at that exact point. So what we eventually do is we take two y values, and remember, y values are a value of the function at a certain x value. So if we zoom in a little bit on our graph here, we take some x and some x plus h, and we find the y values that go with those. And then we can subtract the two y values, and then likewise the two x values we can also subtract. Well, what if we could make this h, because notice the x values disappear from each other, and so the slope then is this. What if we could make that h value smaller and smaller and smaller and smaller until eventually it reaches 0? Well, that leads us to the concept of a limit. In order to be able to work with limits, we have to use this derivative of a function, which again uses the concept of a limit. So let's begin with a simple function and define this idea of a limit. Let's consider what we're going to call the limit of the function f of x as x gets closer and closer to 2. Well, we can approach 2 from two directions. So here I've made a chart of the values. As we start at 1, find the value of f of 1 for this particular function, we get 4. And then we move closer and closer to 2 with each iteration. And what we say is that as the function f of x approaches, as you can see here, it approaches 5 as x approaches 2 from the left. And again, we're picturing this graphically. So here's the value 1, here's the value 2. We are coming closer and closer to 2 from the left, and slowly the function is approaching the point 2, 5 as we get there. Now, that doesn't mean that the value of the function is 5, because if you'll notice, when I actually plug in the value of 2 into this function, the denominator goes to 0 and it's undefined, but it gets closer and closer to that value. Let's look at it a little more graphically here. This is a picture of the actual graph of that function. And again, terminology-wise, we are going to write that as the limit as x approaches 2 from the left of x squared plus x minus 6 over x minus 2 is 5. Again, 2 itself is not in the domain, but the value of the functions gets very, very close to 5. We can consider other limits as well. As x approaches different numbers, we can come from the left or right, and sometimes the values are or are not the same. For example, consider this function. We have a piecewise function here, defined between 0 and 4 as 1/2 x, and defined from above 4 as x minus 1. So let's consider these two limits. Looking at the graph, we have x is 1, 2, 3, 4, 5, and so on. And this is read the limit of the function as x approaches 4 from the right. So we're coming in this direction, and we want to get closer and closer to a value of 4 for x. So we're going to travel down the function until we reach 4. And from the right, you're going to see that the value the function approaches is a y value of 3. But notice the function does not actually equal 3 when x is 4. And you can see that in contrast, if we approach x equals 4 from the left, the function actually approaches a value of 2. Using these two concepts, let's then define formally the left-handed limit and the right-handed limit. And what these say is the values of a function get closer and closer to some number k as the values get closer to x from the left, or likewise from the right. Mathematically, we write this as the limit as x approaches a from the left. Again, it doesn't mean that x is necessarily negative, it's just from the negative direction, of f of x equals some value k. And the right-handed limit we define as the limit as x approaches a from the right of x of x. F of x could be some number m. Let's do another example using a graph here. I've already drawn the graph again of a piecewise function. And let's note these different values. Here, as we approach 2 from the left, you're going to notice that we actually approach a value of 4 for the function. But as we approach 2 from the right, the function approaches a value of 2. Notice the actual value of the function at 2 is indeed 4, because that's where the closed dot is. Looking at a value of x equal to 4, as we approach from the left, the function approaches a value of 2. And as we approach from the right, it approaches a value of 4. However, you're going to see that f of 4 is indeed 4. And last but not least, let's look at as we approach x equals 0 from the right. And you're going to see there that this equals a value of 0. And a couple things to notice, just because the limit has a value does not mean it has the same value at that point of the function. And notice there is no limit for the function as x approaches 0 from the left, because the function itself is not defined to the left of 0. All the limits we've discussed so far have had functions that had some sort of problem, a jump in the graph, a hole in the graph. Now let's consider some nice graphs, such as polynomials, where there are no jumps. These limits are actually much easier to calculate in the sense that to find the limit of a polynomial function, you simply plug in the value to the polynomial. Let's do an example here. So we don't even need the graph in this case. If I want to find the limit of this polynomial, it must be a polynomial, I can simply plug in 3 to the function. And when I calculate this, I get a value of 9 plus 9 minus 7, or 11. The limit as x approaches 3 from the left is going to be 11. Plugging in 2 to this function, I get a value of 8 minus 10. I'm plugging in the wrong number, excuse me. Get a value of -2. And last but not least, when I plug in 0, I get a value of, excuse me, I get a value of 3. Again, notice this works when these are polynomials and there's no holes or jumps in the graph. Now let's consider one last opportunity here where we have an unbounded limit. Take, for example, this function here, 1 over x minus 2. What happens as x gets very close to 2 from the left? Again, we're starting at, say, 1.5 and getting closer and closer to 2. Notice this number is going to keep getting bigger and bigger and bigger. It's not approaching a single value. Well, as we look at this graphically, we can see that what's happening is as we get closer and closer to 2 from the left, it's going to approach -infinity. So we read this as the limit as x approaches 2 from the left of f of x is -infinity. Likewise, if we look at as x approaches 2 from the right, it's getting bigger and bigger in the positive direction. And so we write that as the limit as x approaches 2 from the right of f of x is +infinity. In this case, it creates what's called a vertical asymptote. the line approaches this graph, or the graph approaches this line, but it never touches it. To formally define these, we can define these as infinite one-sided limits. If x increases without bound, then we say it approaches infinity. And that positive infinite limit is if it approaches, say, a from the right of f of x, it's going to approach infinity. It could also approach it from the left, and it's still going to be approaching a positive infinity. And those negative limits of f of x, you simply say that it's approaching negative infinity, again, from the left or from the right. And graphically, what you see there is you have some sort of asymptote, and it's approaching infinity both from the right and from the left. And if it's approaching negative infinity, then it's going to approach from both the left and the right. And notice this is the x value of a in both cases. Notice that in both cases, the limit doesn't exist, but rather it tells us the direction in which it is unbounded. As a final example of this, let's consider something like this limit where x is approaching 3 from the left. Notice, to figure out if it's a positive or negative infinity, and we're actually going to be approaching -3, my apologies. When we're approaching -3 from the left, notice that no matter what I plug in here, if it's approaching -3, this is always going to be negative, but very, very small. And when I divide a number here by something that is very, very small, the top is always going to be positive as we get closer to -3. So this is going to approach negative infinity. Likewise, if we look at the second option from here, again, this should be a -3. As we approach -3 from the right, this value is then always going to be positive and very small. This remains positive, and so our limit here is going to approach infinity. Graphically, it may look something like this. As we approach 2 from the left, we're headed towards positive infinity. But as we approach 2 from the right, we're headed to 3. As we approach 4 from the right, we are headed to 3. And as we approach 4 from the left, we are also headed to 3.